My name is Hamza Salim, and today I will be talking about conservation of energy in a pendulum.
So, what exactly is a pendulum? Well, a pendulum is usually a long rope or string with a fixed object attached to the end of it. Now here in my example, I am showing a grandfather clock. And when you set a timer on the clock, it'll start to give auditory cues as well as its pendulum will start to move. Now the pendulum shown here in the grandfather clock is a spherical disc attached to a narrow piece of wood. Now what would happen if I applied a small force to the spherical disc? Well, we can clearly see that it is moving side to side. And we can clearly see that the conservation of energy is also applied here. Now what exactly is the law of conservation of energy? Now the thing is, before we get into that, we first need to look at what type of energies we're dealing with. The first one can be expressed as Eg, or gravitational potential energy. Its formula consists of the mass multiplied by gravity multiplied by the height of the object. And gravitational energy is simply the energy of an object above the Earth. Now our second energy that comes into play is kinetic energy, which can be expressed as Ek. And the formula is 1 over 2 mv squared, m being the mass and v being the velocity. Now kinetic energy is simply defined as an object in motion, or the energy an object has while it's in motion. So what exactly is the law of conservation of energy? Well, to put it in words, it is simply that in a closed system, energy can be created or destroyed, and that all energy is conserved. Now, to express this, I can show that ET is equal to our gravitational potential plus our kinetic EK. Now this will give us mgh plus 1/2 mv squared. Now, to show this in a visual system, I have a little example right here. Now, here is a ball, and at its peak, before it's dropped, its gravitational potential is at its highest, and its kinetic energy is at its lowest. But the sum of them stays the same, it's constant. Now, as the ball drops, its gravitational energy decreases while the kinetic energy increases. But notice here how the sum of both of them is still conserved. Now, what that means is, since it's conserved, we can express it in its final equation, which is 1/2 mv initial squared plus mgh initial, which is equal to 1 over 2 mv final squared plus mgh final. Now, what we have here is our pendulum demo, and it follows almost the exact same things as the previous diagram. Now, let's look at the path of the pendulum. Now, we can clearly see that there is a maximum point and a minimum point. Now, let's choose a point right over here, and let's call this the maximum point. Now, over here, there is the greatest amount of gravitational potential energy, while exhibiting 0 to the least amount of kinetic energy at this point. Now, as it goes down, gravitational potential energy decreases while kinetic energy increases. Now, let's choose a point right here and call it the minimum point. At this point, there is the most minimum amount of gravitational potential energy, while the highest amount of kinetic energy. Now, as it goes back up, kinetic energy is decreasing while gravitational potential energy is increasing. Now, at this point, it's the same exact thing as the first part, where the gravitational potential energy is at its highest, and there is barely any kinetic energy. Now, what we can say about this system is that mechanical energy, or the total energy, the sum of both of them, is always the same, whether if the pendulum is at this point, or this point.
Thank you. Thank you for watching, and I hope you learned something new about the conservation of energy